Hi, this is Gordon Parker from Michigan Tech, and in this video we're going to go into an introduction of PID control. So here's the block diagram that we'll be working with. We've seen this before in some other videos. It's pretty standard. What we have is a controller in D, in the block D, then we have some plant in G. We'll have unity feedback. Here's our reference input, and there's our output. And we'll also consider a disturbance W. Now, PID control is one of the most popular controls out there. And you can find it in a lot of different forms. And let's say that this is our error signal, by the way, and this is U, the input to the plant. Then the output of the controller U, where what I'm doing right now is assuming that W is 0. So U is exactly the same output that's coming out of there. So the output of the controller is U. The input to the controller is the error signal, E. And the PID controller looks like this. It's some gain Kp times a gain Ki over S, so there's our integrator, plus KdS. Now in this form it doesn't look like a transfer function, but I can certainly write it as a transfer function, as a rational function, I should say, like so. Just multiplying the numerator and denominator of all these elements by S. Now it has a little problem here with the order of the numerator being larger than the denominator, and there's practical ways to fix that, but we're not going to get into that kind of detail just yet. Another form of the PID controller is like this. Sometimes there's a gain out front, and then it's written like so. Same thing, three gains, K, Ti, and Td, and we can relate the gains in this form of the PID controller to this form just by noting that Kp is equal to K, Ki is equal to K over Ti, and Kd is equal to K times Td. And one last thing before we go into trying to understand what all these different terms do is let's look at what the compensator looks like in the time domain. We can take this and just put it into the time domain. So we would have a Kp times the error signal, I'll write it as E of t, plus Ki times the integral of the error signal, plus Kd times the derivative of it. And that's equal to U of t. Now, here's how we're going to sort out what all the different terms do. We're going to do it by example. So let's consider the following plant. So G of S is equal to 1 over S, S plus 1. Kind of a simple plant. And then what we'll do is we'll cycle through different variations of the PID controller. So we'll look at just a proportional controller. That's just Kp with Ki equal Kd equals 0. So we call that a proportional controller. And we've seen a lot of those before. And then we'll go ahead and look at a PI control. So that's where we'll have a Kp and a Ki, but we'll go ahead and set Kd equal to 0. So that's a PI. Pretty popular. And then we'll go ahead and look at the whole PID controller, where all of the terms are non-zero. So we'll just call this 1, 2, and then 3 is the full-up PID. Now what we're going to be doing is only specific to this plant. Okay, so these results are only for this plant, but they give us a little bit of insight into the general behavior of the different terms. Okay, so let's have at it where we do just proportional control. Okay, so Here's what we're going to do, by the way, for all of these. We're going to look at both the transient behavior and the steady state behavior. So let's start with the steady state behavior for KP. So here's my controller now, KP, and I have this, and I have this. Feedback, an R, a Y, and a W. Okay. Now this is a nice system. It's unity feedback, so we can look at it and to assess our steady state behavior. So for instance, just by inspection, we can see that it's type 1 with respect to the reference input W, and it's type 0 with respect to W. Did I say W there? It's type 1 with respect to the reference input R, and type 0 with respect to the disturbance input W. So, and we can draw that conclusion just by looking at the poles at the origin of these two pieces. So if I add up the poles at the origin in both of those two transfer functions, that gives me this system type. And if I just focus my attention on the poles at the origin of that transfer function, it gives me this system type. And that's only because it's unity feedback. Okay, so it's type 1 with respect to R. So what that tells us is that if I give it a step input, it will have 0 steady state error. And if I give it a ramp reference input, it'll have a constant steady state error. And we can actually calculate the ramp steady state error would be equal to 1 over the velocity error constant, kV. And kV is equal to the limit, as s goes to 0, of d times g, where this is d and this is g. So kV is just kp, the proportional controller gain. Now, of course, this implies or assumes that the system is closed loop stable. And we'll look into that a little bit, but for now, let's just assume that it's closed loop stable. So our steady state error is 1 over kp when I give it a ramp input. So what this tells me is, as I increase kp, it drives down the steady state error for a ramp input. Okay, so now let's go ahead and look at the steady state error for a disturbance input. Now there, we know it's type 0. So if we hit it with a step in this disturbance, it's going to have a steady state error. Well, let's go ahead and calculate all that. The error is always R minus Y, and for disturbance, a disturbance input analysis, we set R equal to 0, and we just get this. Now, the y over y over w, which is the transfer function of interest, is just g over 1 plus dg. So that would be 1 over s squared plus s plus kp. And so the error function, E, is just negative 1 over s squared plus s plus kp. And the steady state error is the limit as s goes to 0 of s times E, which in this case would be negative 1 over kp. Again, I have this relationship of 1 over kp. So as I increase kp, I'll drive down my steady state error for the disturbance input. So in both cases, the reference response, steady state response, and the disturbance steady state response, the effect of increasing kp is to drive down steady state error. Makes the system more and more accurate. Great. So there's the steady state analysis. Now let's look at the transient. Percent overshoot, rise time, all that sort of stuff. Okay, and the way we'll do this is we'll just extract the characteristic equation that we had on the previous page and take a look at the closed loop poles as kp moves around. Before we do that, notice that we have a nice second order system. I can compare that to the standard form of a second order system and realize that if I equate those terms, I have 1 is equal to 2 zeta omega n, and Kp is equal to omega n squared. What this one tells me is that zeta omega n is equal to 0.5. Now let's look at the closed loop poles in the complex plane. Zeta omega n of 0.5, if this is negative 0.5, says that the closed loop poles are always going to be along this dashed line, no matter what I do with Kp. Now, this tells me that as I increase Kp, omega n increases. Now, omega n is this distance. So what this means is, as I increase Kp, my closed loop poles are going this way. And what that means, so I'll just sort of carve this out and say this is the direction of increasing Kp. I don't know what a D is doing there. Increasing Kp. Well, if my poles go up this way, zeta, which is related to this angle, right? If I call this angle theta, then the sine theta is equal to zeta. So as I increase Kp, sine theta decreases and zeta decreases. So that means that percent overshoot goes up. The settling time, which is roughly 4.6 over zeta omega n, would roughly stay constant. Now as my zeta gets small, that approximation maybe isn't so good, but as long as I stay around 0.6, 0.7 or so, that approximation is decent. I could also look at rise time, which is about 1.8 over omega n. Again, as Kp goes up, omega n goes up, the rise time goes down. That's consistent with the system becoming faster and faster, just like the percent overshoot going up is consistent with the response, the step response, becoming faster and faster. So there we go. That first term of the PID controller, the Kp, when you increase it, overshoot goes up, the rise time goes down, the response becomes faster, but steady state error decreases. Now, let's go on to PI control. So now my compensator D looks like Kp plus Ki over S. And I could write that as Kps plus Ki all over S. The quantity D times G in the forward path is equal now to Kps plus Ki over S squared, S plus 1. Now some amazing things happened here. First off, because I picked up an extra S in the compensator, the system is now type 2 with respect to the reference input, and it is type 1 with respect to the disturbance. So the act of the integrator increased this type of the system. Now I can hit it with a step in the disturbance input, and I'll have 0 steady state error. I hit it with a ramp, and I'll have constant steady state error. Similarly here, I can now give it a parabolic input and have a constant steady state error, and a ramp would give me 0 steady state error. Now if we just look at this for a little bit longer, if it's type 2, it means that I have an acceleration error constant, which is equal to the limit as s goes to 0 of s squared times d times g, everything in the forward path. And so what this gives me is Ki. And the steady state error to a parabolic input would be 1 over Ki. And what this says then, just like in the other case of the proportional controller, as Ki goes up, my steady state error goes down. Great. So the integral action, the integral term in the PID controller, improves our system type, gives it better disturbance rejection properties, better tracking properties, and it has the same qualitative effect on the steady state error that we do get, that as we increase Ki, we'll drive down steady state error. But Now let's look at the transient response. And what we'll do here is just look at y over r, the reference transfer function. So we have kps plus ki over s squared s plus 1 plus kps plus ki. That's a plus. So I can write that as kps plus ki over s cubed plus s squared plus kps plus ki. Now, I have a cubic in my characteristic equation. Let's pull that out. And to investigate the transient response, what we'll do is just look for stability. Well, let's analyze the stability of this thing, because if we can find values of Kp, Ki where it starts going unstable, then that tells us that we're heading towards a region where the response is very erratic, likely rather fast. So I pick up my 1 and my Kp from there and there, and my 1 and my Ki from here. I'm doing a Routh array. My this term, the S1 term, is Kp minus Ki over 1. That's an I. And this last term is Ki. That's an I. So for stability, everything in this column has to be positive. What that means, assuming that Ki is positive, that Kp minus Ki has to be greater than 0. Let's look at Ki. That means that Ki has to be less than Kp. Now this is not for all PID controllers. This is only because of the particular plant that we're looking at, the 1 over s times s plus 1. Now, so Ki has to be less than Kp. Well, what happens when Ki equals Kp? In that case, this row becomes all zeros. And that means that we pick up an auxiliary equation made from this row, which would be s squared plus Ki. And when that happens, in the complex plane, the closed loop poles are on the imaginary axis, because the roots of this A of s are also roots of the original characteristic equation. And they're complex at the square root of Ki. Not complex, I mean, well, they are complex, but they're actually imaginary to the tune of plus minus square root of Ki. So there they are in the complex plane. So that's when Ki equals Kp. So now we see that what's happening is that the closed loop poles are heading off this way as Ki becomes larger than Kp. Ki less than Kp, our closed loop poles are over here somewhere. Ki greater than Kp, they're over here. So what this tells us is that if we get too large with Ki relative to Kp, the system goes unstable. So the basic effect of increasing Ki for this particular plant, and for a lot of systems, is that it can lead to instability. And it can make the step response, for instance, faster than what you would get with just having proportional control. Now, on to the last piece. Now we'll do PID. So our compensator D is Kp plus Ki over s plus Kd s squared. And even though this form is a little bit disturbing, since the numerator is higher order than the denominator, but we'll just leave it that way for now. It all works because our plant is a sufficiently high order. So here's our forward path, our loop transfer function in this case, is Kd s squared plus Kps plus Ki over s squared s plus 1. We still have type 2 with respect to the reference input, and type 1 with respect to the disturbance input. So adding in the derivative term did not affect our beautiful system type effects that we obtained when we just added the integral term, and we had the PI controller. Now, our closed loop transfer function, with respect to the reference, KDS squared plus KPS plus KI divided by S cubed plus 1 plus KD S squared plus KPS plus KI. Great. Now, we've already covered the steady state response, but now let's take a look at the transient response by probing stability a little bit. So let's see, we pick up from this characteristic equation a 1 and a Kp, a 1 plus Kd now, and a Ki. Now this term, the S1 term, is Kp times 1 plus Kd minus Ki over 1 plus Kd, and down here we have Ki. So this column has to all be positive. What this says is that, let's see, 1 plus Kd has to be greater than 0. So Kd has to be greater than -1. Well, usually we have positive constants. And this one tells us that Ki is greater than 0. Great. Positive. Okay. So now we can just look at this. Kp times 1 plus Kd minus Ki greater than 0. Let's look at it from the Ki perspective. What this says is that Ki has to be less than the quantity Kp times 1 plus Kd. Now this is very similar to what we had on the previous page. When we didn't have Kd, we had the requirement that Ki had to be less than Kp. But now that we have Kd in there, we can actually increase Ki, because Ki just has to be less than Kp times the quantity 1 plus Kd. So as long as Kd is greater than 0, it tells us that we can actually increase Ki. So one way to think of Kd is it provides a bit of stabilizing behavior to the compensator. It moves those poles a little bit away from the imaginary axis if our Ki was close to being equal to Kp for this particular plant. But in general, that's true. Kd gives a little bit of a stabilizing effect. Now just one last set of comments before we wrap this up. I'll just call these other features, and maybe put features in parentheses because these might be considered negative features, but they're features. So let's look at the Kd term. Okay, in the time domain, that's really Kd times E dot, the derivative of the error signal. Now the error signal is formed from the reference signal minus the measurement, the sensed quantity of the output y. So if y is noisy, if this sensor was noisy, that means that E may be noisy, high frequency, non-y noise on that signal. And if that happens, then oftentimes you have to back off on Kd to keep that noise from propagating through the system. So in the previous slide, we saw that you can increase Kd and give yourself some stability. But if that signal is all noisy, if E dot is extremely noisy, then you really can't increase Kd as much as you might like. The other term of interest is Ki. Now that looks like Ki times the integral of the error. Imagine what happens if you give the system a unit step. Boom, like so, and it was sitting down here at 0. So let's say this is our reference, and now I'll draw the output y. So it starts coming up like this. Well, as it's doing that, it gets up to here. As it's doing that, a bunch of error is accumulating, and that error is being integrated and held onto. So that means that the response is going to have to overshoot in order to reduce that error, in order to get rid of this stored error that it integrated. And that's another way to think of why the integral term can give us that oscillatory behavior. This has a name. It's called integrator windup. And it's something that you often have to deal with. You have to actively mitigate the effects of integrator windup, and there's many ways of doing it. And those, of course, are called anti-windup strategies. And depending on your application, you might pick one or another integrator anti-windup strategies. If this delta is too large, this integrator winding up, holding on to that error term, can actually lead to the actuator saturating, hitting its maximum value. And then that leads to some rather unexpected closed loop performance. So just to summarize, did a quick introduction to the PID controller and looking at the 3 different terms for a particular plant. So again, this is Gordon Parker from Michigan Tech, and thanks for watching.